Okay, so let's start the session. So it's my pleasure to present to you now Rainer Hillenbrand. He's a research professor at Nanogune, a research institution in the Basque Country, San Sebastián. So he's going to talk about infrared nanospectroscopy. So it's a pleasure for us to receive him. He's one of the pioneers in the field. So besides he's very young, but he's a very important person in this field, and he's going to show some of his developments in this field and also some perspectives for us.
Yeah, thank you very much, Raul, for the kind introduction and for the invitation to come here. I also want to thank the whole organizing team. So it's very impressive to see what is going on in this field, particularly in synchrotrons. For me, this is particularly interesting because me by myself, I'm not really working with synchrotrons. I'm working on this field of what we call infrared terahertz nanospectroscopy and nanoimaging. And via this tool, I got into contact with synchrotrons. So this is what we developed since more or less now 20 years, and we also commercialized this tool. And Raul was actually one of the first ones who brought this tool, he bought it and brought it to this place here. And because of that, we are in contact with each other. So yeah, I'm coming from San Sebastián in the Basque Country. So for the ones who do not know where it is, so Basque Country here in North Spain at the border to France, city called San Sebastián, very nice city. And this is a rather new institute. It's close to 10 years old. It's called Nanogune. Gune is a Basque word, means location, so place where nanoscale technologies happen. We are about 10 groups, each group around 10 to 15 people. So it's really small compared to what we see here. And these are the different labs here. It is really very diverse, ranging from nanobiotechnology via magnetism to devices, and I'm in charge of nano-optics. So, I will cover a lot of different aspects, and of course many people are involved. I think all the names here they are not all names listed here, so I want to thank particularly the people at the Nanogune, my postdocs and PhD students and collaborators. Then I want to highlight Fritz Kallmann, with whom I started. He was supervising my PhD thesis. Then together with Fritz and my students, we funded Neospec GmbH in Martinsried, close to Munich. Now close to 10, no, we had already 10 years anniversary. And then all my collaborators with Frank Coppens, we work on graphene a lot in the meantime, and with many other people. So that's a brief outline of the talk. As said, I want to cover different aspects, and the idea is that I go through different technical developments, and each development I connect with a slightly different application. So I want to start with an introduction to infrared nanoscopy, or you could also consider it a tip-enhanced infrared near-field microscopy. Then the next development step was what we call nano-FTIR, so Fourier transform infrared spectroscopy with nanoscale resolution. That's why the nano is in front. Then very recently, we turned this tool from a point spectroscopy tool into a hyperspectral nanoimaging tool. Then I would feel naked without talking about synchrotron stuff, but as I cannot show slides by myself, I have slides from other people, particularly Raul was so kind to give me some slides. Then I want to talk about something that is rather interesting application, namely mapping ultra-confined infrared waves in graphene. This is something where also activity here. And then emerging techniques and methods, and I'm not sure whether I can cover this last part here, which is showing that this tool is really quantitative, that eventually could lead one to nanotomography. Okay, let me start. So why is infrared interesting? Well, infrared, I mean specifically the range between mid-infrared, near-infrared to terahertz. So most important application is chemical mapping, because the infrared photon match molecular vibrational energies. So that's why chemists like this tool. But there's much more. Solid-state physicists like it because these photon energies match with crystal lattice vibrations, so one can learn about structural properties. And also very interesting and exciting, one can excite plasmons in doped semiconductors and graphene, and one can use this to learn something about exotic properties of matter, but also more simpler stuff than, for example, mapping in a contact-free fashion conductivity in semiconductors. So the problem is, as you for sure all aware, wavelengths are really long, between 10 and 100 micrometers, so we are diffraction limited. 10 to 100 micrometer is the focus spot of such beams. if you want to see single molecules, and that would be our dream, then we need to beat this by orders of magnitude. And this is what we are doing, and we achieve with a technique that is called scattering type scanning near-field optical microscopy. And that goes back to development around 1995 by Kawata, Bukhara, and Vikramasinghe, at that time at IBM. And so the basic idea is the following. We take a standard atomic force microscope tip, then we shine light on the tip, and we collect the backscattered light. And by doing so, in this early work here published in Science, they claim 7 angstrom optical resolution. And Fritz Kallmann, then my supervisor, he brought this technique to the infrared in '99, showing here spectroscopic contrast of 2 polymers. So just light scattering at an AFM tip, and that gives the resolution. I want to show you now what is the physics behind that and what is the technology we use. So that's a numerical simulation done by my colleague Javier Esparrua in San Sebastian. And it shows a metal cone here, 1 micrometer long, which is illuminated by a beam of 118 micrometer, that's terahertz, with a polarization it can be projected on this axis here. And what happens is that the terahertz field, it drives a current here. The current, of course, is oscillating here. Charges are squeezed into the tip apex with the terahertz frequencies. And that gives rise to a very strong field concentration, field enhancement. It's, you can imagine it as a lightning rod effect, if you want to see it like this, like applying a static voltage to a sharp metal tip here. And because of that, the incident field is concentrated at the very tip apex, and you can see here this zoom in. This happens on the scale of the tip radius. So in this case, about 50 nanometer. Also, we have 180 micrometer wavelengths. This is only depending on the tip apex radius. In principle, if you make this tip atomically sharp, you could focus down to one atom scale, and this has been done with the tip-enhanced Raman experiments, actually, in the visible spectral range. But I want to focus here on the infrared spectral range and elastic light scattering in particular. So this nanoscale concentrated light field we can consider as a nanofocus, if you want to see it like this. The only thing we need to do is we need to bring it close to the object of interest that what we want to image. And so that's easy because that's a scanning probe technique. The tip is typically scanned across the surface, so this is naturally what we are doing in AFM. So if you bring the tip now scanning some objects here, we shine light, then this nanoscale spot illuminates only this object, but not the other one. If you now collect the light scattered from the tip here, we detect only information from this object, but not from the others. So that's the very basic principle behind. So the idea is that the scattering is modified due to a local so-called near-field interaction between the tip here and this object here. So this microscopy technique is always based on near-field interaction. So this is a little bit more artist point of view. We have here the tip, typically 10 micrometer long. Then we have here the laser beam focused to a diffraction limited spot size, about lambda. That's 10 micrometer, that's 10 micrometer. And then we have our nanofocus sitting in the center of this diffraction limited focus. We collect the backscattered light. And here the problem starts, and we solved this problem over many years. And I will show you on the next slide how, but first to the problem. So you can imagine that the volume from which the light scattering occurs is much, much smaller than all the light that is illuminating the tip shaft and the sample here. So we have a huge amount of background. And that was one of the major problems in the very beginning, to extract the light that is scattered due to this nanofocus here. And we do it the following way, and that is now a typical setup that we also commercialized via NEASPEC. And it's as follows. We use a standard atomic force microscope. We developed it by ourselves, but it operates like a standard one. We use standard cantilevers. So you see an SEM here, light microscope image. That's the few hundred micrometer long cantilever, the 10 micrometer long tip. This is here. The tip is fixed, the sample is scanned, and then this tip is oscillating at a mechanical frequency omega. That's called dynamic mode or tapping mode. This is a crucial point, as you will see later on. So now we take a laser, or it could be a synchrotron. We focus that light with a parabolic mirror on the tip, and we collect the backscattered light. Now we do this with the help of a Michelson interferometer. So we have here a reference beam. And this reference beam has several functions. First of all, it allows us a coherent detection. So we get amplitude and phase information. This is very important. And we can use it later on. If we come here with synchrotron or broadband radiation, we can use this setup as a Fourier transform spectrometer. So by just moving this mirror here over a long distance and recording interferogram. And then we collect this interfering light beam here. So the light scattered from the tip is interfered with the reference beam, and we detect it here. Now, another trick is that, or the major trick is that we demodulate this detector signal here at a higher harmonic of this modulation frequency. And to explain that would take too much time. Just should believe me that this higher harmonic demodulation is actually the trick to extract the information that comes from this tiny little nanofocus here out of this background. So, and it's in the end the combination of this interferometric detection together with this so-called higher harmonic demodulation technique that gives us access to the nanofocused light here at the tip apex. So that's an early example that we did. We looked at a test pattern that was an implanted structure in silicon carbide. We looked at it with a visible microscope, so you see here some of the squares here in the range of micrometer can be resolved. That's a simulated image at 10 micrometer, and you don't see anything because of diffraction limit. Then we take this sample, put it in a microscope, we collect the light scattered at the AFM tip here, 10 micrometer wavelengths from a CO2 laser, and you can nicely see all the squares here down to 200, 100 nanometers. So it shows already this big difference here in between diffraction limited imaging and our kind of super resolved imaging based on near-field microscopy. Then based on actually, it was this paper, semiconductor industry got interest in this technology, and they were asking us whether we were able to look at transistors to eventually detect carrier density, strain, and defects. And that was done with Infineon Technologies in Munich, a semiconductor company in Munich. And we looked here at a transistor device from the 65 nanometer technology. So that's the transistor. Here we have gate, drain, and source. That's the channel here of 65 nanometer length here, so it's really small compared to the wavelengths. And then we have here metal contacts, doped areas, and dielectric materials. Then we image that at 10 micrometer wavelengths, and we can very clearly see here these bright areas. This is the metal, because principally it functions very similar to a standard microscope. Metal is highly reflective, and for that reason, if you place the tip above a metal, we get a lot of backscattering from the tip. That's why the metal appears bright. So lower the dielectric of the material onto which we place the tip, the less of this nanofocus is reflected and modifies the tip scattered light. And that's why these dielectrics here, like silicon or silicon oxide, appears dark here. So the contrast here resembles very much the contrast in a reflection type microscope. So then we just switched the laser. Instead of a CO2 laser, we used a terahertz gas laser, and we imaged the same device, exactly the same device again, and we see a similar contrast here. Most impressive, if you take a line profile here, we get a resolution of about 40 nanometer. So that means we beat the diffraction limit by 3 orders of magnitude here. So now this image, you may say, oh, this looks a little bit blurred. Resolution must be worse. No, this is not the case. You see these areas here, they are as bright as the metal. And the reason for that is that these are the red areas here. This is doped silicon. And it's so highly doped that silicon behaves metallic at terahertz frequencies, but it behaves dielectric at infrared frequencies. And this is because the carrier concentration is here in the range of 10 to 18 carriers per cubic centimeter. So if you do spectroscopy, we are mapping out the resonance frequency of these electrons in the semiconductor. We can do contactless carrier profiling. And we actually have a project at the moment with the semiconductor industry to go further in this direction. All right, so these are the different things that I partially will cover, partially not. So this is the technique, and we have gone through many different applications. I mentioned this semiconductor device imaging here. Contamination detection is interesting, but also carrier profiling. Then it's also interesting material science. So this is an indent in silicon carbide. So we press a diamond tip into silicon carbide, and we crack and strain the material. What happens is that the lattice vibrations, the phonons, they shift. And because of that, we get an optical contrast in the near-field image. And what you see here is in the bright areas are compressive strain fields, and this tiny little dark area here, which you don't see in the topography image, that's a crack where we have tensile strain. So I don't want to talk about that here, but that's an interesting application. Also difficult to get quantitatively out the strain fields. Then we can apply this, of course, for chemical mapping. I will talk about this in more detail, so don't say more about this. And another application is to look at not material properties, but at nanoscale light fields in photonic nanostructures and in, for example, graphene, and I also will talk a little bit about this. So as I said, we commercialized the tool, and that's how it looks. It's actually this type of microscope. Actually, you can see in Raoul's beamline here. So we see here, it's pretty small. It's maybe this size here. That is the sample holder here. Sample is located here. Now we zoom in. And we see now the tip coming up here. So that's the tip here. Here we have a sample. Now the sample is scanned like in standard AFM. Then we shine the laser beam here. And we collect the backscattered light. And you see, once the tip goes over highly reflective areas, we get more scattering. If you're on these darker areas, we get less scattering. And then it's like a scanning probe technique, similar to any other scanning probe technique. So the image is put together point by pixel in the computer then. Okay, that was the old version. In the meantime, it looks like this. We tried to get into industry and also make it more user-friendly. So the microscope that you have seen here now is this part here. And all the lasers, broadband lasers, monochromatic lasers, all now in this box. This is now the size of, not much larger than a standard FTIR spectrometer that you can buy. All right, so up to now I've talked about imaging, so I want to point out these were single wavelength images done with monochromatic lasers, so either gas lasers or quantum cascade lasers. Now the next logic step, of course, is to do spectroscopy, and our idea was, well, the most simple broadband source is a thermal source, and it was actually Florian Hood, now working at Neospec, and is the head of research there and development. Well, he came up buying this €100 coil that is heated up to 1000 Kelvin. And then we project this thermal source onto the AFM tip, and we collect the backscattered light, and using this Michelson interferometer as a Fourier transform spectrometer. And after a painful time for Florian, we got some images. So that's an image of two oxides. Here the interface of the oxide. If the tip is at a fixed position, at a white light position, then we get an image. We can clearly see that we get nanoscale resolved image. Then we can place the tip on A and B, two different positions, and we really got some spectra, pretty noisy, but we see that the two oxides are different here. So this is a pretty tough experiment. It's not very practical, and I would not recommend to do it. And so we gave this then up pretty quickly, particularly because Fritz Kallmann came up with a much better solution. Namely, he, based on some developments that are going in the laser field, he developed or set up this device here, which is a difference frequency generator. So where near-infrared supercontinuum is mixed with telecom wavelength laser of high power in a gallium arsenide crystal, and due to difference frequency generation, a laser beam comes out here, which the output spectrum is shown here. So the spectral bandwidth of this infrared beam here is around 500 wave number, and it can be tuned by the laser settings and by the crystal orientation. And the power that we get here, in the meantime, this laser improved, and the moment we get around 1 milliwatt in this spectral bandwidth. And I have a slide later on where I compare to synchrotron. So now this is our broadband light source. We illuminate the tip. And now to get a spectrum, we do the following. The tip is fixed at the sample position, and then we move this mirror here, and we record an interferogram. And this is exactly what you do in a standard Fourier transform spectrometer. We record this interferogram here, and then we Fourier transform it, and we get the spectrum. And these are the spectra here. This is on a polymer, and we get now an amplitude and phase spectrum. And that's the difference to a standard Fourier transform spectrometer. In a standard Fourier transform spectrometer, you have the sample outside the interferometer, so either in front of the detector or in front of the beam splitter. And then you get only the intensity spectrum. But we place the tip and the sample intentionally inside the interferometer, and because of that we get both amplitude and phase information. So we get amplitude and phase, and this is important if you want to get the complex valued information about a sample. And you will see later on that the imaginary part of the spectra is related to the absorption. Also, we have here a scattering experiment. Yeah, so this we can see here. So the first experiment we did is we placed the tip on a simple PMMA layer, and we record a spectrum. And we get an amplitude and a phase spectrum, but what we plot here is the imaginary part, right? So we see here these lines that resemble an infrared spectrum. Then we took a few micrometer thick PMMA, made a transmission Fourier transform experiment, and we record the spectrum. And now we can compare directly, and we see that the peak positions, the peak heights even, they match very nicely. And again, what we observe here is what we find empirically is that what we define as the nano-FDR absorption, namely the imaginary part of the scattered field here, recorded as a function of frequency, it correlates with the far field absorbance, actually. And so we can directly compare. We don't need even to do modeling. Also, the scattering process is a rather difficult one. And so we can just take the spectra, go to a database, to literature, and we can immediately identify, well, this is PMMA. Again, I want to point out, this is a scattering experiment, and we measure absorption here. This is for some people surprising, for other people it's totally normal. This is because we have the phase, and phase always stands for a resonant absorption process. And this is why we have direct access to absorption. So that was then on the same sample, we found this particle. That's an atomic force microscopy image. That's the height. We see here a layer, and here we see a particle sticking out. And that's the atomic force microscopy phase image, which kind of gives us a mechanical map of the sample. And we see that this particle seems to be different. It seems to be neither PMMA nor silicon, so it's something different. And it's rather difficult to say from these atomic force microscopy images what it is. But now having infrared spectroscopy at hand, we can place the tip at A and B and record spectra. On A, we get, again, this PMMA spectrum. But on particle B, which is only 100 nanometer away, we get here completely different spectra with bonds that we can associate with the PDMS. It's kind of silicon. And it happened that the sample was simply contaminated, and we really didn't know it, and afterwards found out that it's absolutely normal that there's PDMS on this sample. Yeah, point out again, the resolution that we achieve here is in the range of 100 times better than with a standard FDR microscope. Okay, so I want to stay with this technique, but switch the application. Now I'm going to biology, to protein spectroscopy. Proteins are peptide chains that are folded into so-called secondary structure, and the most abundant ones are alpha helical structure and beta sheets. The alpha helical structure both appear naturally, but in certain cases, in diseases, if protein misfolding happens, in diseases like Alzheimer and Parkinson, it happens that this alpha helical structure turns into these beta sheets, and then the proteins start to aggregate. And it's rather important to understand these folding processes, and it would be interesting to study that on the nanometer scale. And this is difficult to study that. However, infrared is a very interesting probe to study this. And here you can see the infrared spectrum of the so-called amide 1 band here for alpha helical structure and for beta sheets. And this peak here actually traces the CO double bond here in both cases. But because of the different secondary structure, we have a huge shift of about 10, 20, 30 wave numbers. So it's really a significant contrast. But up to now, this could be only done on a microscale level. So the idea was, or the question was, can we do that on a single protein level? So the first we did is we wanted to look for a small object, but we didn't want to go for a single molecule because we know we don't have yet single molecular sensitivity. So a colleague recommended this single, well, it's a protein complex, but it's a single one. This is ferritin. It's the particle that stores iron in our body. And it has a 9 nanometer ferrihydride core, and it's surrounded by a 2.5 nanometer thick protein layer. And one knows from X-ray structure that it consists of 24 protein or subunits, and it corresponds to 5,000 bonds. That's a really small amount, and it's 12 nanometer in diameter, so we can easily recognize and identify individual particles by topography imaging. That's the topography image. Here we see 3 particles. And we placed the tip on the red spot here, and we took a spectrum. And this is the red curve here, and we see nicely these 2 peaks corresponding to this amide 1 and this amide 2 band. And then we did a far-field experiment of an ensemble, probably billions or millions of these particles, and we get the blue spectrum. And we get a really nice matching here. So then we can choose with a single wavelength. Here we choose a quantum cascade laser. We use this wavelength here, and then we take an image. And then we see that we get a strong absorption contrast for these two particles, but not for this particle here. So we know here's a protein, and this particle here, obviously, it does not absorb at this frequency, so it's obviously no protein. And now if you measure here carefully, you see this particle is smaller. And obviously this particle is not an intact protein complex, but it's just the core. And this fits actually very nicely. And I have another image that we took some scans before, and this particle was absorbing. And so the particle became smaller, so obviously either we heated it up and destroyed it, or we disassembled this particle by scanning, and then this contrast vanished. So in principle, what we have here, in principle, we measure the protein functionalization of a single particle with only a diameter of 12 nanometer and 2.5 nanometer thickness. So it's a really rather sensitive technique already, and so we are confident that we can push this to a single molecular level, but there are a couple of things like photon flux and maybe the sharpness of the tip needs to be improved. So regarding resolution, then we scanned a purple membrane. That's a protein membrane. It's about 7 nanometer thick. We took spectra at each pixel here along this line profile, and we traced this amide-1 band here. So each spectrum at each pixel here, and we go in 10 nanometer steps. And this is a spectral axis, and this is the frequency, so a spectral spatial plot. And we scan along here, and we see here nicely this peak. It persists until we reach the edge of the protein membrane, and then it vanishes pretty quickly within 1 step, more or less. So if we trace the intensity of the peak, we get this line profile here, and we see that within 30 nanometer, we go from 100% signal to about 0% signal. So we have here resolution of at least 30 nanometer, depending on the criteria. We could eventually even claim 10 nanometer resolution that we have here. All right, so now alpha beta, that was the question that we wanted to answer. So we did a physicist-like experiment, biologically not very relevant, I have to say already. So we just took some structure that are well characterized as alpha or beta sheets. And we know that a Tabak mosaic virus, it's a very robust structure, and it's essentially alpha helical structure. And we mixed it with insulin aggregates. Insulin is a model system for protein aggregation. And so we just took insulin monomers, we heated them a little bit, put some chemicals to it, and then these insulin monomers are known to fibrillarize and form aggregates. And so we mixed the stuff together and put it on a silicon substrate. And so we have here the topography image, we have these elongated structures, here's the virus, and here these aggregates. But difficult to say if you don't have chemical information. So then we took monochromatic images. This is a frequency where we expect the beta sheet to absorb, and we see that all these structures indeed show a strong absorption. And then we switch to 1660 wave numbers, and here we know that the alpha helical structure is strongly absorbing. And we see, again, all the structures are absorbing, but here we have a particularly strong contrast. It indicates already we probably have more alpha helical structure here than in the surrounding. So to get the final proof, we did nano FTIR, now placing the tip at the green and the red spot here. And we take nano FTIR spectra. And this is what we get for this location here. We get this amide-1 band, clearly located at 1660 wave numbers, very clean. We have more or less only alpha helical structure. Then we go to the green spot, and we see at this alpha helical position, we get a shoulder here, but we see a strong peak coming up here at around 1635 wave numbers, which is very strongly indicative of beta sheet structure here. So this insulin is now completely folded from alpha to beta, and that's the reason why we have here this slight shoulder here, but we have a significant amount of beta sheet structures here. Yeah, so that is something to be explored further. So we have not gone further in this direction. Sample preparation is definitely an issue. Need to consider that we need to try this at the moment. All these experiments I show are done in the right environment, but we currently started a project to do all this in liquid, and it seems to work. Also, there are a lot of problems to be solved still. Okay, so that means nano FTIR is ready for applications. This was our own work. Then here I want to show you, this is here a work by Fritz Kallmann, and they showed submicron phase coexistence In pentacene molecules, they see here that the ordering or the structural ordering of these pentacene molecules leads to spectral shifts, and they could identify of domains in these pentacene films where the ordering of the pentacene molecules is different. And that's a rather exotic application. This is from Dmitry Basov's group. That was done on stardust and meteorites, and here they look at phonons in meteorites, in minerals, to identify the chemical composition in minerals. So a vast variety of possibilities. One can look at nearly everything that one could look at with a standard infrared microscope. All right, so that was point spectroscopy combined with imaging. Of course, the best we could do is getting a spectrum at each pixel. And this is what is done in far-field methods. It's called hyperspectral imaging. You also do that with the synchrotron radiation. And this is what we wanted to try. But we should keep in mind that the spectrum takes many minutes. So that was a big challenge then for us. And we have only a limited spectral bandwidth with our laser. So nevertheless, we tried it because we wanted to see, is it feasible at all with current technology? So this is a setup the same as we showed before. And now the only thing we did is we scanned, instead of taking a point spectrum, we took a spectrum at each pixel, or more precisely, we take here in an array of about 100 by 100 pixel, we take interferograms. And so each interferogram is Fourier transformed, and then we get a hyperspectral data cube. So the problem is we have a bandwidth limited laser. If you want to have a broadband spectrum, we need to detune the laser. So we did the following. We took these data cubes here at 3 times at different laser settings. So at 1, 2, and 3. And so we have here this overlapping spectral coverage. So we take data cube 1, data cube 2, data cube 3. Then we have these 3 data cubes, we Fourier transform them, and then we stitch these 3 cubes together. That is, of course, connected with a lot of challenges. So we need a very stable laser, very stable scanning, and so on. So there were a lot of tricks involved, but finally we got it done. And it took, each cube here took about 2.5 hours. So one spectrum about 2-3 seconds. And so as we have to stitch it together, altogether the whole acquisition time was about 7.5 hours. And then we get this nice hyperspectral data cube here. And then we see here different images. If we slice at a certain frequency, and then we can slice through this cube, we see how the contrast evolves, and the signal to noise is already pretty good. So this was a couple of years ago. In the meantime, laser technology has evolved, and also the electronics and hardware of the NEASNOM improved. And now we can record actually spectra with a medium resolution in about 100 milliseconds, and it's possible to get such a cube in 20 to 30 minutes. So we are coming closer to the goal of doing regularly hyperspectral imaging. Also, there's a little bit of way to go. So this is how it looks if we go through this data cube in frequency. So now we slice through. And you can see that the signal to noise is already pretty okay to get some meaningful information out of that. So the sample that we looked at here was actually a 3-component polymer blend. It was 40% fluorine copolymer, 40% of acrylic copolymer, and 20% of polystyrene. And the image contrasts are already rather complicated. And so we were wondering whether our data are good enough to apply standard multivariate data analysis. So we applied that, and we used here a technique that it's called interspectral distance mapping. So we take a reference spectrum on the 3 different materials that are composing the sample here. And then at each pixel, we compare the reference spectrum with the actual spectrum at the pixel here. So the reference spectra of this fluorinated polymer and the acrylic copolymer are the black ones. And here you see a different spectra here. Each spectra is from 1 pixel, and these are 6 or 9 neighboring pixels here. So you see already that the spectra are pretty reproducible and stable here. So now we calculate the spectral distance between the reference spectrum and the spectrum at each pixel, and then we get these red and blue maps here. And this red color indicates here once a spectrum is very similar to this reference spectrum here. And so we can get a map that indicates us the distribution of the acrylic copolymer, and here the fluorinated copolymer. And we see that they are at different locations. We can overlap these areas, and then we have the blue areas indicating the FP, the red areas, and we have these black areas here. We couldn't find any agreement, and the reason is that we have here very likely the polystyrene, and for the polystyrene, we didn't get actually a good spectrum because the vibrational signature of polystyrene is rather weak. So that's why these areas are black here. But in the end, it shows that without any significant data processing, we can do standard multivariate data analysis and get these compositional maps here. So actually, we could identify here these purple areas, and this is rather interesting. In these purple areas, we couldn't get any agreement to any of the initial components, not even by making a linear superposition. And talking to chemists, this could be indicative of chemical interaction at the interface between the polymers, giving rise to bond shifts that cannot be explained by just a superposition of the spectra. I don't have time to talk about that. So this could be also very interesting to study chemical interaction at interfaces of polymers and any other material, with nanoscale precision, of course. Okay, so now coming to synchrotron-based nano FTIR. So this I think this work with the glow bar thermal source inspired a couple of people. I guess this was also the reason why here the interest was growing in this technique. And so also other groups started to work on that. And actually the first group who demonstrated nano FTIR based on synchrotron was in Berlin around the Gerhard Ulm. So they published this in 2013. And then paper came up in 2014 from Markus Raschke and Hans Bechtel and Michael Martin, and they combined a home-built system based on a Bruker spectrometer and a Bruker AFM. They combined that with their ALS synchrotron, and they get a very nice broadband spectra here. In this case, they looked at a biomineral, and they could see here very clearly the interface, in this case, between calcite and aragonite. And they have in this paper also this comparison here, where they calculate the spectral irradiance here. For a black body here in black, then what they have at their synchrotron, that's the red line here. Then they plotted in here, this is our laser. You see we have more power, but we are much more limited in spectral bandwidths. And then that's another laser, I think that's from Markus Raschke's group. So one can push the power even better, but the current trend is the more power a laser has, the more narrow band it is. So there's still a lot of interest, and I think it's really a lot of potential for synchrotrons because lasers become powerful, but they don't cover yet this full spectral range that the synchrotron could cover. And for that reason, I think it's still a good thing to have a near-field microscope or spectrometer at a synchrotron. So now that's a slide that I got from Raul yesterday. So that's the setup that is installed here. So the infrared beam is here transferred via some beamline primary optics to a beam splitter. Then this parabolic mirror is used to focus on the tip. And then we have here the interferometer. So this is the microscope, and that's the optics that, as far as I understood, was developed here to bring this beam nicely to the parabolic mirror and get a stable imaging capabilities here. This photo I took yesterday, this is actually how it looks. You remember that is the microscope, and here the whole setup, and this guy you all know. Okay, so yeah, and a lot of interesting work has been done here already, so now the next slides are not my own. This is all what I got from Raul, but I think it would be nice to highlight to show what is going on here. So I go briefly through it. So there's some activities going on by performing nano FTIR spectroscopy on 2D materials, and one example is here boron nitride, and boron nitride is an interesting upcoming material. It's important for encapsulating graphene, but it also has intrinsic infrared active phonons supporting infrared waves. So I will come to these confined light fields in 2D materials a little bit later. Then they also showed here that they can perform broadband spectroscopy. Here, PMMA spectrum here that is much more broadband, so that's one spectrum, while in our case we have to stitch that together by 3 laser settings here. They also started to work on proteins. Here, a broadband spectrum that shows the amide-1 band here of what was it, neurons, right? So also seems to work very nicely. Signal to noise is good enough, and certainly has enough signal to noise to distinguish between alpha and beta sheets. And yeah, this is some ongoing work. So here, work on 2D materials. That's a really emerging field in nanospectroscopy, because these materials have a lot of interesting infrared response that requires nanoscale characterization here. And I cannot go into detail. That's Raoul's work, so I leave it with this. And there's a slide showing a little bit the future. So this nano FTIR spectrometer will be installed at Sirius, and the beam will be hopefully better and give better signal to noise. And the idea is to bring it there to also implement hyperspectral imaging to look then at cells. I think I've even seen some images yesterday of cells, and this also seems to work already. And yeah, I think I'm really looking forward to see the first results. And I think this is a great opportunity that you have here to combine this tool with this powerful new light source. All right, so then I would like to come to some topic that goes away from material science, but goes more into the field of photonics, and photonics with 2D materials. And there was a huge interest recently after the first papers were published on this. Namely, we talk now about infrared waves, kind of light waves that propagate in graphene sheets. A graphene sheet is a monolayer of carbon atoms, so it's really thin. But theory predicted actually in the year 2008, 2009, as far as I remember, they predicted that a graphene sheet, if it is doped, can support electromagnetic waves that propagate along the sheet as guided waves. So they propagate along the sheet, but their field is exponentially decaying perpendicular. So a monolayer of carbon atom should work as a waveguide without doing anything. It just requires that the graphene is doped. And by solving Maxwell's equations for this two-dimensional electron gas, that you can consider it, they came up with an amazing prediction that if one compares the photon wavelengths to the wavelengths of this electromagnetic wave in graphene that is called a plasmon polariton, then the wavelengths of these plasmons should be 100 times smaller than that of a photon. That means you shine infrared wavelengths on graphene, you convert it into this electromagnetic wave, and you get a wave that has the energy of infrared light, but the wavelengths of UV. And that is interesting because now one could think of making optical or photonic circuits based on these waves. So in principle, we can shrink down optics by a factor of 10 to 100 by just squeezing light into this graphene sheet here. So, and there's of course a lot of interest in that because it has a lot of potential for sensing, for biosensing, nonlinear optics, building nanophotonic circuits. And the reason is this enormously short wavelengths. And to give you a feeling for it, I show you here some numerical calculations of an electromagnetic wave. That's the electromagnetic field distribution that propagates along this thin stripe here. That's the graphene sheet, and that's the electromagnetic field that propagates here. At different Fermi energies, that means at different dopings of the graphene layer. And you can see already that the wavelengths here, the oscillation period changes as a function of the Fermi energy and of the doping. And the doping in graphene can be adjusted simply by putting a backgate below the graphene. So by applying a voltage, one can change the Fermi energy, and then the wavelengths of the light that you squeeze into the graphene sheet is changed. So you have the possibility to, first of all, squeeze light down to a deep sub-wavelength scale, and secondly, you apply a voltage and you change its wavelengths. That's fascinating and has been predicted. And here for comparison, that's the graphene plasmons. So this is one wavelength of these plasmons, and that's half the photon wavelengths. So this is what has been predicted. Now we have two problems. First of all, we have a huge momentum mismatch. We cannot just focus a photon onto a graphene sheet. There's a huge momentum mismatch. We will never excite a graphene plasmon in a standard reflection experiment, not even with any other trick. And the other thing is, once we excite these graphene plasmons, how do we image them? Because the wavelength is much shorter than the photon wavelengths. So and here our microscope comes into play. We now use this near-field focus created by the metal antenna here to do both, to excite and to image these waves. And the idea is as follows. We take the tip, place it on top of the graphene sheet. We shine 10 micrometer wavelengths on the tip. We create this nanofocus. Now, if you think of this in terms of momentum distribution in this focus, we will have a lot of near-field components with a very high momentum because we are deep sub-wavelength scale. And there are components with a momentum that match that of the graphene plasmons here. Then the graphene plasmon propagates away. This is kind of a point source, like throwing a stone into water. These waves would propagate away from the tip. So that's the way how we excite them. But how do we image them? Because they just propagate away. We image them by scanning close to a defect or the edge here. These waves exist only inside the graphene, but not outside. So if we scan close to here, the waves will be back reflected and giving rise to standing wave pattern here to interference phenomena. And so we imaged here graphene sheet that was epitaxially grown in silicon carbide, and then we see indeed these fringes here that are parallel to the edge here. And these fringes are nothing else than the standing wave pattern. And the distance here between two fringes is half the plasmon wavelengths, like in a Fabry-Perot interferometer-like experiment. So if we measure that, we come up with a plasmon wavelength of 230 nanometer. Also, the photon wavelength is 10 micrometer. And that corresponds to a wavelength compression of lambda over 40. So that's quite impressive. And this actually triggered a lot of interest in the field, and there's a lot of potential. Now these waves don't propagate very long because this was done with graphene that was not of the highest quality. But if one uses graphene that is embedded in boron nitride, this is high mobility graphene with mobilities that are enormous, then we see here that these fringes persist much more, and we see here many oscillations. So these graphene plasmons propagate over many hundreds of nanometers, that means over many wavelengths, but still they are damped out. I mean, these are not like free space photons. These waves have a certain damping because they are heavily coupled to the electron gas itself. Nevertheless, we get here 500 femtosecond lifetime, and if one compares that to a plasmon in a metal, in the visible frequency, then this is a factor of 10 better. So these waves don't propagate very long because they are extremely slow. So the group velocity is about 1% of the group velocity of phase velocity of light. Then just want to give you another example. So I mentioned already, the Fermi energy determines the wavelengths. And so we did the following experiment. We took this sandwich here. And here we have the graphene, boron nitride, silicon oxide, and below is silicon. And we can use this silicon as a backgate. And that's schematically shown here. Here's the boron nitride graphene sandwich. Then we have a gold contact, and we use the silicon as a backgate. And then we can change the Fermi energy or the doping in the graphene here. And so we did the following. We now scan to an edge here, and we see these fringes here. So that's the edge of the graphene, and we see the standing wave pattern in this direction. And in the horizontal axis here, we plot the voltage that we apply here. And so we get, here we have a spatial coordinate, and here we have the voltage. And what we see is that these oscillations here, the spacing between the peak to peak here, it gets narrower and narrower. And that means if we reduce the voltage here, we shrink the wavelengths. And from this real space image, we can now measure the wavelengths of these plasmons as a function of the carrier concentration. And you can see that with a voltage in the range of a few tens of volts, we can change the wavelengths from about 70 nanometer to about 120 nanometers. So a quite large tuning range with a few tens of volts. That's the one thing. And the other thing is here we have 70 nanometer, and the imaging wavelengths here again was 10 micrometers. So this shows electrical tunability of these waves plus a very strong confinement. And so this has a lot of potential to build optical circuitry And SNOM is here definitely a tool to study the basic properties such as wavelengths, how long these waves propagate, and so on. All right, so time is running, so I come now to this part. Probably I should stop after that. I also mentioned terahertz, and the terahertz is also triggering a lot of interest. But in terahertz, we have a couple of problems. So terahertz wavelengths are really long. We're talking about 100, 200, 500 micrometer wavelengths. And so if we scatter light at this 10 micrometer long tip, then the scattering efficiency is very weak. That's the first problem. And the other problem is that detectors in the terahertz spectral range are typically bolometers, but bolometers are very slow. And remember, we oscillate here the tip and do higher harmonic demodulation at several hundreds of kilohertz, and that is not really good for bolometers, so they cannot detect this light. And anyway, scattering efficiencies are weak. So that's a problem. This is why this technique evolves very slowly. And so another possibility is to use a near-field detector. And in this case, we use graphene. And don't go into detail. So that's a graphene sheet, and this graphene supports plasmons. But if one creates a PN junction by having here a split-gate architecture, one can create here a very strong change in the Seebeck coefficient. And we would then have a local light source, like the ones provided by our nanofocus here at the tip. We get a local heating of the graphene sheet, and that gives rise to a photocurrent in the graphene sheet. And this photocurrent we can measure here with these two lateral contacts. So in principle, this device here is a terahertz photodetector. But what we detect now is not far-field radiation, but we detect the near-field intensity at the tip apex. So, and this is this device that we scanned now here. And what we see here is that's a photocurrent image. So the photons come in here and creating a current, then we scan here and we get this photocurrent map here. And we get an amazing signal to noise here because we directly detect the near field. We don't need to go back to the far field. And this is one possibility to increase the sensitivity. That may be also interesting with synchrotron radiation. Now, the fascinating thing then here is that we scanned this device here, and here we see that's the active area here where all the photocurrent is generated. It's an area of about 1 micrometer. We shine here a spot size of 100 micrometer, and we get here this high photocurrent generation, and we see that we get a resolution here in the range of 50 to 100 nanometer with this technique. But then if we scan close to the edge, we have seen actually these modulations in the photocurrent. And this we could identify then as terahertz plasmons in the graphene sheet that propagate in the device. Now the graphene is the material that supports the plasmon. This is the one that we want to see, but we use the graphene itself as a detector. So, and that's a very nice possibility to avoid the use of far-field detectors and increase the signal to noise. So these are indeed plasmons. We can see here if we change the frequency, we see that these wavelengths, peak-to-peak distance here changes, and we have here wavelengths of 1 to 2 micrometer. Also the photon wavelength is more than 100 micrometer. So it shows we have these exotic waves not only in the infrared, but we also have them in the terahertz spectral range. Well, then another possibility or another thing to do is to optimize tips. So at the moment, we use standard tips. So the 10 micrometer long, we buy them, nothing is optimized. And as I said, the wavelength is huge in the terahertz, and then these tips are really much too short here. So then we adopt concepts from radio wave technology. We just make these rods here, or these tips here, as long as lambda over 2. In this case, we can expect a resonant excitation. So this works like a radio wave antenna, just now for terahertz waves, if we make this long enough. And so student Stefan Mastel, he did this by FIP fabrication, rather sophisticated technique. So he cuts away the standard tip. He cuts out with FIP a long metal wire up to 100 micrometer long. We can make it as sharp as 10 nanometer or even better. And we can adjust the length here. And then this acts, we can do AFM and we can do imaging. And we can get actually these resonances here. So here we we measure the photocurrent. We place this tip above the photodetector, and we measure the photocurrent as a function of tip length here, and then we see these oscillations. We see that the photocurrent goes up dramatically if we go to very long tips, We performed the numerical simulation here, and we could identify these peaks here. These are the fundamental antenna resonance here, and this is the second order resonance here. And so I think this is another thing to do, engineering these tips and making them better. That's another possibility to get out more photons in an experiment. And then very quickly, this is work from Dmitry Brasov. They brought this to low temperatures. So the whole thing can be done at low temperatures. Maybe also interesting here. What they studied here is by heating up, this was V2O3, which is an insulator at low temperature and turns into a metallic phase. And everything that is red here is metallic, everything that is blue is dielectric, and they could see that here a kind of nanostructures grow out during this phase transition, and this can be done at low temperatures. So also an interesting tool for material science. And actually NeoSpec, together with AtoCube, developed now the first low temperature commercial near-field microscope. It's available, a bit expensive, but so you may consider it for the future. And with that, I think I come to the end here and summarize here. So yeah, over the last years, we developed a technique we call scattering type scanning near-field optical microscopy that in combination with spectroscopy leads to nano-FTR spectroscopy. This was one of the first things we developed. Then this can be nicely combined with synchrotron radiation. It has a lot of applications. And I did not show this. People and groups like Dmitry Basov or Rupert Huber, they combine that with ultra-fast pump probe technology that also works. Then we can get nanoscale spatial resolution and femtosecond temporal resolution. Low temperature is already there and can be done, and other groups combine this technique with a terahertz time domain spectroscopy. That's a technique for itself, but again, this technique also suffers from the weak radiation. And I think at this moment I should stop and thank you for your attention and again for the invitation.
Thank you, Rainer. So this was a very impressive presentation, and I'm sure it will inspire a lot X-rays folks to visit the infrared beamline, maybe, right? So some questions?
Hi, thank you very much for a very nice talk. So, you know, as an outsider, I see some similarities of this technique with, you know, tip-enhanced Raman spectroscopy. Maybe, do you think there are problems that could be attacked by any of these techniques? And in this case, do you see one of them outperforming the other or are similar?
Okay, so it is more or less the same. So we call that scattering type near-field optical microscopy, but in the end, I think a better word would be tip-enhanced infrared microscopy, because we use metal tips, and these metal tips make a field enhancement, and it's exactly the same as people do this tip-enhanced Raman spectroscopy. The difference is we do elastic light scattering, and in tip-enhanced Raman, you need one laser, a visible laser, and you get the whole spectrum at once, and this is inelastic scattering. So the problem in tip-enhanced Raman scattering is that the performance signal to noise is rather weak. That's a problem, and so the community suffers a lot from irreproducibility, and it's difficult. Also, I have to say that there are amazing results. People achieve submolecular resolution with TERS that we have not achieved yet. So they go to STM and high vacuum, and so there's a lot of interesting results going on, and it's amazing, fascinating. But the community, I think it's difficult to go on more macroscopic rough samples like polymers and so on, because in tip-enhanced Raman they make a lot of use of putting metal below and then have thin layer of molecules to get a strong field enhancement because of tip metal substrate coupling. If you go to polymer samples, like industrial polymer samples that are thick, micrometers thick, or hair, we look at hair, for example, we had an example, I didn't show it here. These are big macroscopic samples with a lot of topography, and tip-enhanced Raman is more difficult there. But our technique is pretty good there. It's rather robust. And we have a lot of collaboration with industry, and industry tells us that they tried tip-enhanced Raman, but they're not so happy because it's difficult, it's very often irreproducible. for these type of samples. But if it's about molecular resolution, tip-enhanced Raman is much further advanced than our technique here. So I would like to bring that, and many other people do, I guess, to molecular resolution. I think it's doable, but here the problem is that this elastic scattering. So if you have a single molecule below the tip, we will always see the tip-substrate coupling, which gives a kind of a huge background in which the molecular signature sits. If you do tip-enhanced Raman, you put a notch filter in the beam, and the tip-substrate coupling and the signal arising from that, you filter out. And then you have, let's say, the Raman signal that comes from the molecule below the tip, and then you have this on a background-free signal. And we have always this elastic scattering that comes from the tip itself and so on. I think these are the difference between the two techniques. But I think the question of stability, and maybe some people come up with some tricks to push this further. But I think macromolecular level should be doable. But they're complementary techniques. We implemented that just recently, Raman spectrometer in our setup, and it works. And the next step we want to do is trying to combine. Selection rules are different between Raman and infrared, and so I consider it as complementary rather than as competing. And then, you find applications where Raman is better, for other infrared is better.
Okay. More questions?
Thank you very much. It was a very impressive talk and very inspiring. Can you give us an idea if the future of the technique could go three dimensions or?
In 3 dimensions?
Yeah.
Okay, that is the last part that I skipped. Very briefly, so the idea is that we also want to apply modeling and reconstruction. And so the first we did is, we collect the backscattered light, and this is not really, it's some scattered light. We want to get epsilon out of it. And so the idea is the following, and it works. We take a model for this tip scattering process, and then we reconstruct real imaginary part of the dielectric function. So this is kind of in a fashion of nanoellipsometry. And this is how it works. We take the spectra, then we have a model here, and then we reconstruct. And actually, I don't have no time to go into details, but the red spectrum here, that's the real and imaginary part of the dielectric function. In the background, we have ellipsometer data of this PMMA film. The point is, this is a heavily nonlinear problem. To invert that is rather tricky. So this is ellipsometry. And then the other thing is, then we look into depths. So here we look at gold particles that go into depths, and we can see that even if they are deep, we see them, but they get blurred and they slowly vanish. But we look into depths. And that was the reason why we came up with the idea of doing nanotomography based on a reconstruction. And the idea is here. So like in any tomography, if we scan, we get a kind of a projection. So we need independent multiple images of the sample. So in tomography, normally you take your sample, you get different projections, you make back projection via radon transform or whatever. But this is all linear. In our case, everything is nonlinear, and that makes it extremely challenging. The other question is, we need different projections. We cannot rotate the sample here. So what we are doing, or the concept is that we oscillate this tip here at a certain frequency, and then we demodulate. And we can demodulate at 2, 3, 4, and 5 times of the modulation frequency. And it can be shown mathematically that these images are independent. And so by kind of inverting the whole problem, which is super difficult, we tried it for 5 years. I had a theoretician who was really expert in near-field tomography, and we didn't get it done in a global fashion. But here we got a reconstruction of this interface here. So we scanned a silicon oxide wedge above silicon wafer, and then we get the reconstruction. Well, it's not really tomography, but we could localize this interface here. So that's a cross-section. That's the AFM signal. This is the permittivity that we reconstructed, the color here. It codes for refractive index or dielectric function. And this line here, that's the interface. And that took us a long time, this specific sample. This is not something that I would sell as tomography yet. It will take many, many years, and many more people need to work on it. But in principle, the possibility is there.
But you're restricted then, in this case, number of projections to the number of harmonics.
Yes.
So
that's exactly
what makes it difficult.
Yes, that's the problem. We see up to the 5th harmonic, And so we will never get a high resolution. I mean, in tomography, you can make the more projections you have, the better. And here we are limited to these projections. It's a signal-to-noise question. The point is that this first harmonic in signal strength is orders of magnitude weaker than the fifth harmonic. And this is because we lose signal in depth because this tip-sample interaction is highly nonlinear with distance. And the signal decays. And so the deeper we go, if you give that back into the reconstruction, all the noise gets into the whole reconstruction and makes it unfeasible.
Could you use different frequencies for the tip for increasing?
At the moment, we try to combine that with other techniques. So, for example, if you do spectroscopy, then we see that if you have an object going deeper and deeper, you get spectral shifts related to its location. However, this shift may be of chemical nature, so you don't know. So it's getting tricky. So there's a lot of potential, but I think it's super complicated.
How about combining something, some concepts like OCT, optical coherent tomography, with this technique? Because in OCT you have the depth profile.
Yeah, but here the point is that here we are, this range here is here, 40 nanometer, right? We are deep sub-wavelength scale. We cannot look deeper. So we could look deeper by making larger tips, but then we lose resolution. If you go to 1 nanometer sharp tips, we wouldn't look deeper than a few nanometers. So that's a drawback. Spatial resolution and depth resolution are coupled. So this is a surface-sensitive technique that has the capability to probe a shallow subsurface layer, which is always on the size of 2 or 3 times the tip radius, but not more.
Thank you very much.
More questions? So if not, let's thank the speaker again.